welcome to ADO. We're going to be implementing guided backpropagation from scratch using Python and PyTorch hooks. And I know what you're thinking. Don't they have a package for this? Well, this approach is going to give us a lot of flexibility when it comes to applying the method. Specifically, we're going to look at how to compute and interpret guided backpropagation gradients in 3 ways. These are the gradients of a target logit with respect to the input. This helps identify which parts of an image contribute most to a class prediction. Of a target logit with respect to the intermediate feature maps. This helps us understand the role of different layers in the network. And of an element in a feature map with respect to the input. This reveals the spatial properties of abstract features learned by deeper network layers. Each of these approaches offer a unique benefit when it comes to interpreting a model. And as we go, you'll also see that they provide an intuitive understanding for how convolutional neural networks work and how methods like Grad-CAM can use the spatial nature of feature maps. Before we get started, I'd like to mention that this lesson is part of a wider explainable AI course for computer vision. It's completely free and you can find a link to it in the description. You'll find the article version for this lesson as well as many coding resources. There's also a paid version of the course which I'll talk about at the end of this video. Okay, so we're working in the guided backprop notebook in the gradient folder. And yeah, we're going to start with our imports. Pretty bare bones. We kind of have like standard matplotlib, numpy, perl to kind of work with images. And then we just have our PyTorch functions and a little request function because we're going to be downloading some stuff for the ImageNet dataset. And yeah, so we're going to be working with a model that's pre-trained on ImageNet. So we have a few functions here just to help work with that model. So the first is going to process an image so that it's in the correct format to input into the model. Some standard stuff here like transforming the image. These mean and standard deviations come from the ImageNet dataset. And then we have the display output. So ImageNet has loads and loads of classes. Just to make things a little bit more manageable for us, we're going to kind of output the top n, or by default the top 5 classes with their predicted probabilities. And yeah, we have our example image that we're going to be working with. So I actually took this image on a recent trip to Japan. It's from a sushi bar. And yeah, ImageNet doesn't have a class for sushi, so it'll be quite interesting to see what the model predicts this image as. And then yeah, we can load our pre-trained model. In this case, we're going to be working with VGG 16. We move that to a GPU and set it to evaluation mode. Okay, and yeah, we have our sort of model summary, and the names in the summary are quite important. So, for example, features.5 are going to give us this convolutional layer, and that's the 3rd convolutional layer in the network. And that just allows us to sort of reference specific layers in the network. And another important point is when we go to apply guided backpropagation, we will be editing these ReLU functions using the ReLU masking process that we spoke about in the theory lesson. Okay, so next we are going to get a prediction for that example image that we just saw, and then calculate gradients using standard backpropagation. This is going to be useful to compare to the gradients calculating using guided backpropagation later on. Okay, so we're going to process our image so that it's in the correct format for this model, move it to a GPU, and then we're going to clone this image. And we do this because PyTorch does this thing where it accumulates gradients if you do kind of like multiple backwards passes. And we want to avoid this just because it can lead to misleading visualizations. So kind of before we do any operation, we're just going to start from a fresh image just to kind of avoid any unwanted mistakes. And then we also need to enable the gradient tracking on the image tensor. And by default, when you do a backwards pass in PyTorch, it will only calculate gradients for intermediate layers because those are the layers where we want to update the parameters. But for the input image, we typically don't, there's no parameters to update. So by default, PyTorch won't calculate gradients. But in this case, we want the gradients for visualization purposes. And then, we kind of feed that image into our model to get a prediction and then format that image to show us the top 5 predictions. And you can see our top prediction is for a grocery store with close to 30% probability. And I think given all of the possible classes in ImageNet, this kind of makes sense. It kind of looks like a grocery store with some sushi or food on a table. Okay, so now we are going to do our backwards pass. And again, we're going to reset the gradients of the model. This is just to avoid any accumulation of gradients. We want to do the backwards pass from a specific class of interest or logit of interest. In this case, we're going to use the highest predicted logit. So we get the index for that class, which is going to be the grocery store class in this case. And then we do backwards propagation or the backwards pass starting from this logit. Okay, so PyTorch in the background would have calculated all those gradients for us. And to visualize them, we are going to extract the ones from the image tensor. So we just reference the grads. Then we detach them so they are separated from the PyTorch computational graph. And if we kind of manipulate or change these gradients in any way, it's not going to impact the original model or computational graph. And you can see that the shape of these gradients are 1 for our batch size of one image, 3 for the 3 different channels, the RGB pixel channels, and then each channel is going to be 254 by 254 pixels, and that's just how we've resized this image. And before we move on, it's worth clarifying what these gradients are and what they can really tell us about the model or the prediction. So we've calculated the gradient of the target logit, or in this case the logit for grocery store, with respect to the input image. In other words, these tell us how a small change in a pixel's value will impact the target logit. And pixels with larger values would be expected to be more important to the prediction for this logit. Okay, so to help visualize the gradients, we have this process grads function, and it does a few things. It can apply an activation function like the ReLU or absolute. For example, we might want to apply the ReLU function because we are only interested in looking at positive gradients. We can also normalize the gradients between a value of 0 and 1. And then we can also skew the gradients so that small gradients are given a greater weight in our visualization. And we can also grayscale so that instead of visualizing the gradients for each channel, we just kind of get an average over all 3 channels. Okay, so we get our gradients, and then we're just going to visualize a few different kind of options from that process grads. We have the ReLU, the absolute, and then we also grayscale. And yeah, you can see kind of similar visualizations in each case. There's a lot of noise going on. You can start to maybe see kind of some important regions, like the table in the image is kind of coming out. Also maybe kind of like the glass case. But yeah, we're going to see how standard, or we're going to see how guided backpropagation can improve on this visualization. So to implement guided backpropagation, we're going to apply PyTorch hooks. And these are pretty powerful functions that allow you to kind of save information at any point in a network, at any layer in a network. And also it will allow us to change how gradients flow through the network. But before we apply those, we need to replace all the ReLU activation functions in our network. Our VGG16 network was created using ReLU functions with in place set to true. These modify tensors in memory so the original value is lost. That is, tensors used as inputs into the activation are overwritten. This can lead to problems when applying hooks, as we may need the original input. Okay, so we use this function, we input our model, and it will replace all of the ReLU activation functions with in place equals false versions. Now, this is not going to impact the output of the model in any way. It's just going to change its memory usage, and it's just going to increase the memory usage by a little bit. Also, another point, it's important to apply this before you apply any hooks. Otherwise, this will remove any of the hooks that you've applied to the model. Okay, so next we're going to move on to applying, or just walking through the ReLU hook function, which is going to be applied to the ReLU activation functions. And yeah, this is going to do the ReLU masking that we spoke about. So by default, any backwards hooks or hooks you want to apply during the backwards pass in PyTorch is going to have three parameters. So the first is the module, which is just the kind of the layer or the component of the network. Grad in is the gradient with respect to the input into the module, and grad out is the gradient with respect to the output of the module. Then we also have an additional parameter, which is layer name, and that's just the name of the module. And these are going to be the same as those layer names that you saw in the model summary. Just quickly going back to this diagram from the theory lesson, we can get a clearer understanding of these parameters. It is grad in that is passed to the previous layer in the network during the backwards pass. So that's why within this ReLU hook function, we are modifying the grad in. And to do that, we clamp the gradients to 0. Essentially, we're making all negative gradients 0. We also preserve none gradients. Then we're also going to save these modified gradients to a gradients dictionary with the layer name as the key. And this is going to allow us to visualize the gradients of intermediate layers in a future section of this video. And when we save those gradients, it's important to detach them from the PyTorch computational graph, just so that if we make adjustments, we don't impact the actual network. Then, yeah, we return the modified gradients as a tuple. This is just how PyTorch formats its gradients. And yeah, essentially what's going to happen is we are going to now pass these modified gradients through the network and essentially only propagate positive gradients at the ReLU activation functions. And that's ReLU masking. That's what the simple trick that guided backpropagation uses. Then to actually register these hook functions onto the ReLU activation functions in the network, we just have this final step where we loop over all the modules in the model. We get the name and the layer. And if the layer is a ReLU function, we register a backwards hook onto the layer. In this case, we're registering our ReLU hook function. And yeah, if usually you can just kind of pass the function name into this register backwards hook function, but because we have this additional name parameter, we have to use this lambda function. And that's kind of it. Now the model is set up so that it's going to propagate gradients using the guided backpropagation process and not the standard backpropagation process. You can also see when you run this, it will register hooks on kind of specific layers. And if you go back to the model summary, you can see each of these layers refers to a ReLU activation function. With the hooks in place, we can apply guided backpropagation. And to start, we're going to calculate the gradients of the target logit with respect to the input image. And to do that, we follow the exact same process as standard backpropagation. We're going to reset our gradients to avoid any accumulation errors. We're going to get a model prediction or do the forward pass through the model. We're then going to do the backwards pass starting at our class or the logit for our class of interest, which is going to be the highest logit. Okay. So yeah, that's going to kind of calculate all the gradients in the background and also save the gradients from intermediate layers. And also remember, because the ReLU hooks have been activated, it's only going to pass positive gradients through the network. Then yeah, we kind of select our gradients in the same way as before, and we're going to process them using the ReLU activation function. And it makes a lot of sense to use this when working with guided backpropagation, because even though we're only propagating positive gradients, there's still a convolutional layer between the first ReLU activation function and the input image. And so we can still get some negative gradients in that final step. And yeah, we only want to visualize positive gradients. And yeah, we're just going to visualize this next to the equivalent gradients from the standard backpropagation procedure. You'll notice straight away that the guided backpropagation has produced a much clearer interpretation. Looking at standard backprop, we may be able to understand important regions of the image. In comparison with guided backpropagation, we can see edges and objects that are important to the prediction. Intuitively, the different foods appear to be contributing to the grocery store prediction. This example shows how guided backpropagation can be used to explain individual predictions of a model. That is, we can see which features in the input image are important to the prediction. This insight can be very useful when it comes to debugging models, but we can also go further and visualize the gradients of intermediate layers in the network. As we saw, our ReLU hook also saves the gradients from intermediate layers. Specifically, these are the gradients of the target logit with respect to the activations in the feature maps. To clarify, going back to this diagram, the ReLU hook saves the modified gradients of the inputs into the ReLU activation layers. These are the positive gradients passed to previous layers in the network. The gradients stored at each ReLU layer will have the same number of channels as the kernels in the previous convolutional layer. Going back to the model output, we saw that features.0 was a convolutional layer with 64 kernels. This means that the gradient saved at features.1, the next ReLU layer, will have 64 channels. Okay, just to show you what I mean, we're going to select this first ReLU layer. We're going to get all of the gradients for this layer and display its shape. And then we're going to select a random gradient or a gradient from a random feature map in this layer, and then just display it. So you can first see that the shape is going to be 64 by 224 by 224. So we have 64 feature maps or channels, and each of them is going to be 224 by 224 pixels. And you can see one of the feature maps in this layer. And just to make things a little bit more interesting, we're going to repeat a similar process, but for different layers in the network. So we're going to start at early layers and then work our way down to deeper layers in the network. And in each case, we're going to randomly print or randomly output 5 gradients from each of those layers. Looking at feature maps like these, we can gain a deeper understanding of how the network works. Like most CNNs, earlier layers detect basic patterns like edges and textures. Deeper layers detect more abstract features like object parts. The deepest layers detect abstract global features that represent entire objects or semantic meaning. Guided backpropagation helps in visualizing this behavior by ensuring that only patterns that have positively contributed to a prediction are highlighted. These kinds of insights go beyond just understanding the nature of convolutional neural networks. They can also be used to improve the performance or efficiency of networks. For example, this paper introduced a method called deconvolution, which is the precursor to guided backpropagation. They use the approach to visualize the first and second layer of the network, identify problems, and adjust the convolutional layer's filter size and stride to correct them. Going back to the general nature of convolutional neural networks, we can clearly see that spatial information is preserved in earlier layers. That is, for features.1, we can see different edges and textures in the same location as the objects in the input image. What is not so obvious is that spatial information is preserved even in deeper layers. We'll prove this using our next approach. Until now, we have visualized gradients of an output logit, but we can actually visualize gradients of the output of any layer in the network. To see how, we're going to calculate the gradients of the output of a convolutional layer or a specific element in a convolutional layer with respect to the input. So to do this, we need to start with a new hook function. We're going to call this the activation hook function. And now this is a forward hook function, so the parameters are different to before. We have our module still. We have the input into the layer, the output into the layer, output of the layer, and the layer name. So this is going to be activated during a forward pass of the network. And all we're going to do is just save the output from the layer to an activations dictionary using the layer name as the key. And then we apply this to every convolutional layer in the network. And again, you'll see that these kind of these layer names correspond to the convolutional layers in the network. Okay, so with the hooks in place, we can do our forward pass, get a prediction, and then our forward hook is going to save all of the activations from the different convolutional layers, and we're just going to select the feature maps from one of these layers, which is features.21, which is quite a deep layer. And yeah, when we output the shape, you can see that we have 512 feature maps, and each of those feature maps is 28 by 28 pixels, because like as the image moves through the network, it compresses in terms of its height and its width. So let's just visualize the first 18 feature maps in that layer. And you can see all the different activations. What we're going to do is take one of these activations from the first layer at position 1414, which is kind of roughly in the middle of this feature map. And we're going to do our backwards pass starting from this element. Okay. And then, yeah, we can visualize our gradients just as before. And now what you see is kind of this highlighted region of pixels in the middle of the image. And before we get too deep into what that means, let's just repeat the same process using different positions within this feature map. So we're going to start in the top left corner, top right corner, bottom left, bottom right. And yeah, just repeat the exact same process that we saw before. You can see the different objects in the input that have contributed to the activated elements. These are made clear by guided backpropagation. Another thing you will have noticed is that the objects are in the same locations as the positions of the elements in the feature map. This demonstrates that although the deeper feature maps contain more abstract features, they still retain spatial information from earlier layers. This property of convolutional neural networks helps explain why a previous method we spoke about, Grad-CAM, works so well. This method creates heat maps by weighting the feature maps in the last convolutional layer of a network. If that layer didn't retain spatial information, the heat maps wouldn't be able to identify important regions in the input image. So, guided backpropagation goes a long way in helping reduce the noise in saliency maps. This is useful when explaining individual predictions or even the general behavior of a network. However, there are still cases where guided backpropagation goes wrong. In the next section of the course, we are going to apply guided Grad-CAM. This method combines both the benefits of Grad-CAM and guided backpropagation. And the result is even clearer saliency maps that show important features in the input image. As I mentioned, this video is part of a larger course where I go into detail on explainable AI methods for computer vision. This includes methods like occlusion, SHAP, Grad-CAM, guided backpropagation, deep lift, and integrated gradients. You can access all of the course content for free, but there's also a paid version of the course. With that, you'll get access to a certificate for the course, quizzes, all of the videos ad-free, and an ebook, which will allow you to access all of the course content offline.